So at this point in Chapter 13, I've gone over the characteristics of light. In this video, I'll be moving on to discuss flat mirrors. Before we can look at mirrors, I'll define reflection. Reflection is the change in direction of an electromagnetic wave that causes it to move away from a surface. So you've probably experienced reflection before by looking in a mirror. However, there are two types of reflection that you need to be aware of. The first is called diffuse reflection. This takes place when light rays reflect off of a rough surface. So I've drawn this sort of squiggly line to indicate that the surface is not completely smooth. And as you can see, when these red light rays go in at the same angle, I've tried to draw these all sort of at similar angles to the surface, they come out at all different angles because the surface is sort of different at each place where the light is coming in. By contrast, there's also specular reflection. This occurs when light reflects off of a very smooth and flat surface, such as a clear lake. In this case, when all the rays come in again at the same angle that I've tried to draw, they go out at the same angle. So you can see it forms all these parallel lines because all of the rays are going in the same direction. So again, the texture of the surface will determine which type of reflection takes place. When light is reflected off of a smooth surface, the reflected light is symmetrical. This means that it reflects at the same angle as the incoming light. The angle of incidence is the angle between a ray that strikes a surface and the line perpendicular to the surface at the point at which it strikes. So I've drawn this black dotted normal line to the surface. And they're saying that this angle here, theta, is the angle of incidence. That's the angle between, again, this light that's striking and this perpendicular line. We also have an angle of reflection. This is the angle formed by the same perpendicular line and the direction in which the reflected ray leaves the surface. That would be the second angle, which I'll call theta 2. And that's between the perpendicular line and this ray that's leaving the surface. In a case where light is reflected off a smooth surface, theta, or the angle of incidence, will always equal theta 2, the angle of reflection. You're probably already familiar with flat mirrors. These are the mirrors that people typically use to look in. In a flat mirror, the object distance, P, which is the distance between an object or a person standing in front of a mirror and the mirror itself, will always equal the image distance, which is how far behind the mirror the object appears to be. I haven't drawn this very well to scale, but in real life, the person standing in front of the mirror would see himself being an equal distance behind the mirror to the distance he is away from the mirror. In a flat mirror, objects are also represented as their actual size. So images that are formed in a flat mirror are called virtual images. A virtual image is defined as an image that forms at a point from which light rays appear but do not actually come. This is why the image appears behind or within the mirror, even when there's no light emanating from the mirror itself. And one final thing to note about flat mirrors is that images in these mirrors are always reversed. So you've probably seen this if you've tried to hold writing up to the mirror. You'll see it backwards when you look in the mirror. So with these characteristics of flat mirrors in mind, let's move on to some practice problems. Number 1. Suppose you are holding a flat mirror and standing at the center of a giant clock face built into the floor. Someone standing at 12 o'clock shines a beam of light toward you, and you want to use the mirror to reflect the beam toward an observer standing at 5 o'clock. What should the angle of incidence be to achieve this? So let's sort of draw the situation. You have this light coming down from 12 o'clock. You're standing at the center, and you want the light to reflect to 5 o'clock, which is roughly over here. I'll label these points 12 and 5. And you also have this mirror in your hand. So the first step would be to determine the angle between 12 o'clock and 5 o'clock. We know that 5 hours on a clock, or this distance, is 5/12 of the total distance around the clock, which is also 360 degrees. We can solve for the angle between these two times by multiplying 5/12 times 360, which is 150 degrees. So we know from the lesson on flat mirrors that the angle of incidence will always equal the angle of reflection, and we want these two to add up to 150 degrees. So essentially 2 times theta, or the angle of incidence, will need to be equal to 150 degrees. So now you can see if I divide both sides by 2, isolate theta, I get that the angle of incidence would need to be 75 degrees. Number 2. Which of the following are examples of specular reflection and which are examples of diffuse reflection? So you might remember from the previous slides that specular reflection occurs on a smooth surface, while diffuse reflection occurs on a rough surface. With this in mind, it should be pretty easy to answer these questions. Part A, reflection of light from the surface of a calm lake. Well, a calm lake is pretty smooth, so we'll say that that's specular. Part B, reflection of light from a plastic trash bag. Although this might seem smooth, trash bags are often wrinkled and don't always reflect light in the exact same direction, so we'll call this diffuse. C, reflection of light from the lens of an eyeglass. An eyeglass is pretty smooth, so that's specular, S. And finally D, reflection of light from a carpet. A carpet should be pretty obviously rough, so it's diffuse. It will not reflect light in the same direction all the time.